finally, let me rewrite this version given in terms of creation and annihilation operators in the P and Q and the Y relations. So in the following remarks, I want to collect the main statements about this. And first of all, I want to go over from this continuous version where I'm indexing my things by functions or elements in the underlying Hilbert space to a discrete version where I want to have a countable number of operators just by taking for the F's and the G's an orthonormal basis, because then these inner products here will be either a 0 or 1. And that's more the usual form which we consider. So for indexing my operators, I take a basis indexed by some elements in index set. So this should be an orthonormal basis of H. And then I denote the corresponding creation and annihilation operators. A of EI, I just denote it by AI. So AI is now just A of AI. And okay, let me now write AI star. This is the A star, or here was the plus of EI. So those guys are adjoints of each other. And now I really want to go over to the Q and the P. And the relation between them was that actually if I'm taking the sum or the difference of the A and the A stars, this gives me the P and Q operators. So I should define the Qi as AI plus A star divided by square root of 2, and the corresponding Pi as the difference AI minus AI star divided by I times the square root of 2. And of course, A and A star are adjoints of each other, so this and also this are self-adjoint operators. And so, I mean, self-adjoint operators are, of course, things we can control much better than a pair of just an operator and its adjoint. So, but you see, in principle, always, if I have an operator and it's adjoint, I can look on the real and the imaginary part essentially of this. So I can replace it by a pair of self-adjoint operators, what I'm doing here. Yeah, and then I can rewrite the relations which I have. First I can write this down here for the AIs. Maybe let me do this. And then we can rewrite it in terms of the P and the Q. Yeah, but maybe first I say that because the Q and the P are unbounded operators, if I say they are self-adjoint, at least they are formally symmetric, that's of course clear, but then one can check that they are really essentially self-adjoint. They are really nice operators. So maybe I write this down. So the Qi and the Pi are essentially self-adjoint. So their closure is a self-adjoint operator. Yeah, but now let me rewrite the relations which I had over there in terms of these operators here. And then we have, first of all, let me just write down again in terms of A and A star. So of course I have that AI and AJ. This always commutes in the same way as AI star and AJ star always commutes. And the interesting part of the relations is what happens if I'm looking on the mixture of A and A star. So what is AI, the commutator, with AJ star? And of course this is now this relation, but here I'm just taking the inner product between the EI and the EJ, and this is 1 or 0 according to whether those indices are the same or whether they are different. So this is just delta IJ times 1. And maybe that's the form which we are more used to for looking on the canonical commutation relations. Yeah, and if I write this, rewrite this in terms of the Q's, then of course maybe it's even more, the relations we are used to. So namely then, of course, the relation between two Q's, this is always 0. Doesn't matter whether I is the same or not to j, and the same for the p's. So the pi and the pj always commute. The crucial non-trivial thing is the commutation between qi and between the q's and the p's. And then again, if their indices are different, they commute. The only non-commutativity happens if the indices are the same. So if I have pi with qj, this gives me minus I times delta ij. So it's 0 if I is different from j, and it's minus I times the identity operator if they are the same. Yeah, and that's the one which we want. Yeah, but as I already mentioned, looking for solutions of or representations of this form is a little bit, not so clear what one really wants, because one has to specify the domain. And just making the obvious conditions on the domain, even in a one-dimensional case, doesn't exclude strange examples which one doesn't like. So what one really wants is to take the unitary groups, because I mean P and Q are now self-adjoint, essentially self-adjoint operators. So I can take the unitary group, and then I really get some nice bounded operators, and they satisfy some relations. That's what we call the Weyl relations, and that's the one of which we want to know whether there is a unique representation or not. So let us look this. Let us look on this. So maybe, so I consider now the corresponding unitary groups. Corresponding unitary groups. So this means I'm exponentiating those P and Q as generators to get, let's say, UK of t. So this is e to the I pkt. So for each k, I take pk as a generator of a unitary group. Of course, this I is just the square root of -1. I get this as a group in T. And I do the same for the P, for the Q. And then I call this the V. So this is Vk of T. This is e to the I qkt. Okay, those guys are unbounded, so this gives me unitary groups which are strongly continuous, which are not norm continuous, but anyhow, it's still a group of unitary operators, and they satisfy some commutation relations. Now, at least formally, one can check what those relations mean for the relations between UK and the V. And so namely, they satisfy now the relations which we call the Weyl relations. So then those guys, then they satisfy the Weyl relations. So namely, I can multiply any of the u's, so I can take UK of t, I can multiply this with any of the v's, so let me take VL of S, and now this commutes up to some unitary factor. So this is VL of S times UK of T, and here I get a factor, and this factor only really is non-trivial, meaning different from 1, if K is different from L. So if K is equal, no, it's non-different if they are different. So if K and L are different, then the U and the V just commute in the same way as here the P and the Q commute if they have different indices. So I get here a factor which is e to the I, and I have here delta of KL. So if K and L are different, this is 0, then this E factor is just 1. And then they commute, but otherwise I get here a phase e to the I delta KL, and I get here S times T. Oh, I mean that's the usual Weyl relation, which we had for the case where K and L are just 1, when we only have one operator. Yeah, and so of course now I can look on this for arbitrary underlying Hilbert spaces. So in particular, I mean I can choose a dimension of this Hilbert space, because I mean the number of variables which I have here is the number of the dimension of my Hilbert space. And if my Hilbert space is finite dimensional, then what I get here is of course the Schrödinger representation somehow in disguise. We know that in a case if I only have a finite number of indices here, a finite number of degree, we know the Schrödinger representation is unique. I mean, as an irreducible representation. So maybe one should also check that the representation which I have here is irreducible, but this is somehow clear because I mean I just generated everything out of the vacuum with the help of my operators. So this means there cannot be an invariant subspace somewhere. Yeah, which decomposes the whole representation. So I have here an irreducible representation of those guys, and if I would have here a finite number of degrees, then I would know that this is the Schrödinger equation. But now the Schrödinger representation. But now, of course, what we are interested is, or what is the nice thing with this construction is that this works for any h. It doesn't matter whether the dimension of h is finite or whether it's infinite. So in particular now, of course, we are interested in the dimension of h as infinity. So I mean this is the number of elements which I have in my indexing set. So this means infinity means I have infinitely many, an infinite number of q's and of p's, or here also of uk's and vl's. And so what we get then is here a realization or a representation. So we get thus a representation of the infinite dimensional version of the Weyl relations, of the infinite dimensional version of the Weyl relations. So just of those relations here where really K and L are just indexed by the natural numbers. And of course, I mean, this is nice on one side because before, the constructions which we did before for the Schrödinger representation, they could not directly be extended to the case of infinite number of degrees. This representation here works always, but of course you could say, okay, infinite number of degrees, we also have the representation, and that's it. There's nothing more to say. But now, of course, maybe not of course, but actually in this case, there's really much more to say, because now this uniqueness theorem of Stone von Neumann breaks down totally, absolutely, in this situation. So this is a representation of the Weyl relations, but actually it's a kind of trivial one, and physically, in physical terms, it's non-interesting one, or I mean it's one which corresponds to trivial situations where one doesn't really have interaction or something like this. So usually what one really wants to construct or understand in quantum field theory are representations of those things which are not equivalent to the one which I have here. And so what we want to do in the next lecture is really to understand that in this infinite dimensional situation, really there are irreducible, there are inequivalent representations. I mean, of course, this is not clear. I mean, we have here one, and so the question is, can we construct more, or can we understand that there are others which are not equivalent to this? And this will actually be related to the question whether I have an infinite tensor product of Hilbert spaces, or whether I have one or more, and how they are related. And so in the next lecture, we will really attack the question of infinite product of Hilbert spaces, but also see that this relates and gives us the idea that actually there are there are much more representations of this one.